Hello everyone, my name is Xiang Yuzhen. Today I'm here to present a mid-demo report for our project IFA Translator. Okay. So IFA Translator is a multifunctional AI-powered translation tool. It supports simultaneous interpretation, live screen translation, document and image translation, meeting translation, and even call record translation. Our goal is to deliver a solution that's accurate, efficient, and secure for cross-language communication. It's designed for scenarios like business meetings, cross-border e-commerce, international study, and something like that. And at the left side is our landing page. Okay. So right now we are focused on Epic One user onboarding, where the main tasks are email-based sign-up and login, Google OAuth third-party login, email verification flow, basic user profile management. This stage sets the foundation for secure access and identity management across the entire platform. And at the right side is our sign-up page for PC. So far, we made a good progress on the backend. As you can see, we have done the user sign up and sign in backend and send verification email to verify user, third-party sign on and login, third-party sign up, the front end and backend, and update user profile backend and something like that. So to summarize, most backend tasks are done, front-end work is ongoing, and we expect to wrap up all tasks by the end of this month. And the next steps, we plan to complete reviews and connect front-end forms to backend APIs, finalize the full email verification flow, kick off Epic 2 meeting translation, which will support real-time multi-speaker meetings and events. And at this point, I'll pass it to Stephen to dive deeper into the technical architecture and implementation highlights of our user onboarding module. And now it's
Hello.
Stephen.
Hi, so today's I'm going to divide my presentation into 4 parts. So the first part is how to using the design the back end and the front end for the Google OAuth third-party authentication, and the second part is like how the email verification is achieved by the user, and then the third part I will just doing a brief summary about how about the technical stack we use at the moment, and the fourth part I will just doing the demo for our system. So the first part, so this one is the design of the Google OAuth authentication on the back end, on the front end. So on the sign up page or sign in page, the user will just click the buttons of the Google authentication, and then the user will be redirected to the Google OAuth page. And then once the user provide the information, and then he will just receive the verification code on their phone. And then once the user was plug in the verification code in the sign up page provided by Google, so they will have a 2 option for that user to reject to provide the personal information or accept to provide the information. So if the user are happy to provide the information to us, so the user will be redirected to the backend callback URL. And then our backend server will using the passport.js and the Google strategy to get the user email name, Google ID, avatar, etc. from the Google. And if the user is not agreed to do that, so the user will be just redirected to the login venue page. So on here, so on the Google, on the backend server, so if the user agreed to do so, so our server will check if there's an existing user in the database or not. So if there's an existing user in the database, so the user will be redirected to the login callback URL with the JWT token to the front end. So if there's no existing user in the database, so the system will create a new user and then to redirect it to the front end with the token. So on the front end, we will just using a really simple API call, which decided by ourselves to get the user profile. And then if the user using the token generated by our system, and then the server response is okay, it means that the token is valid. So if it's not response okay, it means that the token is not valid. So if the token is valid, the user will be redirected to the user dashboard, and if it's not valid, will be divided to the login value page, and then show him he got an invalid token. So the next part, we talk about the email verification sign up. So on the sign up page, user using the normal way to sign up, he put the email name, phone number on the sign up page, and then it will trigger the email sending API route. And then once the user is trigger this API call, so our server will create a new user in the database. That's the first step. And then it will just set the user activated status is false. And also the backend server will create other tables called the verification table, and then to put a new verification token in it. And then this token will be expired in 24 hours. And after doing those two steps, so we were using the no mailer to send the email to the user. And then this email will have the verification link, which have the email verify API combined with the user token. And then once the user is clicked the verification link, so our API will compare the token from the user to the token in our database. So if it's matched, it will redirect it will just activate the user account, and then the user can be directed to the login page. But if the user is not gonna click the link in the 24 hours, so after 1 day, so he need to go back to the sign up page and do the process again because his link is expired. So that's the base summary of the tech stack we use in the last month. So the front end, we're using Next.js, Chakra UI, TypeScript. And the back end, we're using the Node.js, Express.js, Passport.js, NoMelder, TypeScript. And the database, we're using the MongoDB. On the cloud service, we're using the Google Console platform, which used to hosting the front end and the back end API for third-party authentication. And the Google email verification part, we're using the SMTP protocol provided by the Google and using the no mailer to send the email. So next step, I will just do the demos for our system. So that's basically the landing page of our system. We already finished the landing page on it. So because for time saving, I will already register the account myself. And then that's the sign in page. So that is already registered. And then if we click sign in, it will show the sign in is successful, and then we'll redirect it to the user dashboard. And also for the third party login, if we click this button, yep, it will redirect us to the dashboard as well via the third party authentication. And then that's pretty much what we did in the last 1 month. So next, welcome the DevOps teams to give us the presentation. Thank you.
DevOps 同学这边好像听不到声音，大家能听到吗？
哦，忘开麦了。
哦，好的好的，现在
哈哈，
听到了。
好的好的，谢谢。Hello everyone. Today we'd like to present the architecture of our DevOps project, which includes both front-end and back-end infrastructures deployed on AWS using Terraform. Our team consists of 6 members: Ben, David, Zijia, Jesse, Mira, and myself. Let's begin with the front end. The front end is a static site hosted on S3, delivered globally through the CloudFront. We use Route 53 for DNS and Certificate Manager to enable HTTPS with a customer domain, IFA Translation-UAT.click. All components were provisioned using Terraform. For the backend, we have 2 stages. Initially, the backend runs on an EC2 instance inside a public subnet, connected directly to the internet via Internet Gateway. It pulled data from the MongoDB atlas and was managed manually. We use EventBridge and Lambda to automate EC2 start and stop schedules. In the stage 2, we moved to ECS Fargate, which allowed us to run containers without managing servers. Tasks are deployed across 2 public subnets in different availability zones, ensuring high availability. ECS is also highly scalable, allowing us to handle increased traffic by simply increasing the number of the running tasks without changing infrastructure. We added ALB to distribute traffic and perform health checks, automatically routing requests to healthy tasks. All traffic flows through the ALB to ECS containers, which pulled images from ECR during deployment. There are several things we plan to improve in the future. Migrate ECS tasks to the private subnet for the better security. Placing ECS in private subnets ensures containers are not directly exposed to the internet, reducing the attack surface. Add CloudWatch and ELK stack for the logging and monitoring. Set up dashboards and alerts for the real-time visibility. That's all my part. Let Mira to introduce the Terraform.
Thank you, Rocky. Let me quickly walk you through some of the key things we learned while using Terraform. Terraform is powerful because it allows us to define our entire cloud infrastructure as code. It's declarative, which means we just describe the desired state and Terraform handles the rest, whether it's increasing an S3 bucket, setting up permissions, or uploading static files. This simplifies and speeds up the provisioning process. To make development more flexible, we run Terraform locally, which gave us fully control during the testing. We could test change in SIP environments, view plan outputs before applying, and easily track what changes would be made and troubleshoot issues much more easier than working directly in the AWS console. We also use the Terraform modules to keep the setup organized and reusable. These modules communicate with each other by passing data. For example, after the S3 modules creates a bucket, it outputs a bucket name. That output is then passed into the CloudFront model as an input. So it knows which bucket to use as an origin. This way, each module handles its own parts, but they still work together. Using modules really helped us keep the code clean and reusable. It also made everything more organized and easier to understand. In the future, we're gonna integrating Terraform into CI/CD pipelines. Will make our process even more efficient. We will be able to automatically deploy the infrastructure changes as part of our code's delivery process. This ensures a consistency between the environments, reduce manual errors, and helps us move faster with confidence. That's a quick summary of how we use Terraform in this project and what we gained from it. Now I will hand it over to Jess to talk about the Lambda and EventBridge. Thank you.
So I'd like to give you a quick overview of the AWS Lambda and EventBridge. They are the two AWS services we use to optimize our cloud infrastructure and reduce costs, especially during the early stage of our project. So Lambda is a serverless compute service that allows us to run code without provisioning or managing servers. It's highly scalable and event-driven, make it a great fit for the automation tasks. EventBridge is a serverless services that use events to connect applications components. Essentially, it's an event bus that facilitates communication between services by emitting and responding to events. So our main goal here is cost efficiency and reducing operational overhead, particularly because our project is planned to have 3 environments, dev, UAT, and production. Since the team doesn't work around the clock, it makes sense to shut down unused resources during off hours. So to address this, we've implemented 2 Lambda-based automation, as you can see on my slides. The first one is for ECS Fargate containers. So we've created a Lambda function that starts and stops ECS containers at specific times. Since Fargate pricing is based on the requested vCPU and memory per hour, so this helps us avoid unnecessary charges. The second is for servers on EC2. We've set up another Lambda function to start and stop EC2 instances as needed, because the EC2 is built based on compute capacity over time. This also contributes to our cost savings. So these both functions are scheduled to trigger through EventBridge rules, automatically shutting down containers and EC2 instances at 9 p.m. and starting them again at 9 a.m. the next day. So this automation ensures we only consume resources when we actually need them without requiring manual intervention. Now I'll pass my speech to Sijia.
Next, I will briefly talk to you about our CI/CD process for both the front end and the back end. First, I will talk about our Git branches. As you can see, every time the developer team finishes the phase of code review, the branch is pushed to the UAT branch, which is the user acceptance testing. After DevOps teams finish deploying the UAT branch, it was pushed to the production branch, which is the final product. So our CI/CD process is basically using the Jenkins pipeline. It was built on the UAT and production environments. Whenever a code is pushed to GitHub, the webhook triggers the appropriate pipeline. And for the front end, Jenkins runs on an EC2 instance, which handles the whole process. It installs the necessary packages, builds the static files, and installs the AWS CLI, depends on whether it exists or not. Finally, it will deploy the output to the S3 bucket. For the backend, the Jenkins CI is also on the EC2 instance. We built the application and the Docker image. The image is then pushed to the ECR and deployed to the ECS cluster. We also support another direct deployment to an EC2 backend server, depending on the environment. This automatic pipeline ensures a faster delivery of our product. And that ends our presentation. Thank you so much for listening.